and welcome back to another virtual maths session. These sessions have been commissioned by the Councillor for the Bridgeport Division in the Municipality of Portmore, Councillor Kennord Grant, Building a Better Bridgeport Division. Last time, we briefly went through the concept of a variable. We discovered that a variable takes the place of or represents a changeable or unknown value. An equal sign is the notable difference between an equation and an expression. An equation has an equal sign with information on both sides of the equal sign, but an expression does not include an equal sign. We also discovered that we can calculate the value of an algebraic expression by simply substituting the value of each variable in that expression and then performing the calculations that we see before us. Go ahead and take a look at that video before going through this one if you didn't have a chance to before. Today, we'll be exploring the possibilities of creating our own algebraic expressions and equations. But first, today's tip. Online classes are different from traditional classroom experiences. Though it allows us to be comfortable while learning, that comfort can also serve as a distraction. It makes sense then that even our home environment encourages learning. Schedule your daily activities as if it were a school timetable. When you sit for a virtual class, things like chores or errands or even your favorite series should not be happening during your class time. These things can cause you to lose focus and miss out on an opportunity to grasp concepts in a meaningful way. Now, let's dive into it. Sometimes, when we are presented with algebraic problems in a classroom setting, we are given the equation. Other times, we are asked to create the expression or the equation after we would have been given some information to guide us. The reason for this is, as assessors, we need to know that students are able to apply the individual pieces of knowledge they have about different topics to solve problems that may even be real-world scenarios. Basically, if we can create algebraic expressions or equations given set information, we may be able to troubleshoot and solve real-world problems, even those that may not include numbers. Let's begin by examining expressions and equations again. There are elements of each that we need to be able to recognize. Without these elements, we may even say they are not expressions or equations. Let's begin with an algebraic expression. Here are a few examples. X plus 5, p minus y, m divided by 2, x times 4, or 4x. Take a moment to examine each of these. They each are made up of 3 important components. Can you identify what those components are? Let's take a look together. In the first example, we see a variable, an addition sign, then a number. The second has a similar structure, a variable, a subtraction sign, then another variable. The third and fourth examples follow the same basic structure, variables, numbers, and a division or multiplication sign. So we could say then that every expression has variables or numbers and a sign, either addition, subtraction, multiplication, or division. Those four signs are called operations, and they are the four basic operations in mathematics. Therefore, it's safe to conclude that every expression is made up of variables, numbers, and operations. We'll call these the three important components of an expression. Equations have a similar structure. Remember from our last session, we found out that we could build equations from expressions by adding something that does not appear in expressions. Yup, the equal sign. So let's turn our expressions into equations. You will notice that the additional components are an equal sign and a term or another expression on the other end of the equal sign. Expressions and equations can be very simple, such as those in our examples, or they can be really complex, and that usually happens when we have more than one operation involved, or even other operations like indices, or even functions such as tangent, sine, or cosine. No matter how simple or complicated it may appear, the basic idea with all of them is that there are variables and or numbers interacting with each other, usually with the help of operations. So, quick recap. What does every expression need to be an algebraic expression? Variables or numbers or both, and operations. And what do equations need to be algebraic equations? Variables or numbers or both, operations, equal sign, an expression, or just individual numbers or variables on the other side of the equal sign. Now that we know how equations and expressions should look, let's try to create our own. Let's take our first example, the sum of x and 7. Firstly, you will notice that while there are numbers and variables present, it is predominantly words. That doesn't look very mathy, and that's why the instruction is to express or write it as an algebraic expression. The trick is to, firstly, recall all the elements needed to make an algebraic expression or equation. Next, look for them in the statement and write them out. Then, put them together to form the expression or equation. It's just like baking a cake. The raw ingredients are present and definitely do not look like the cake. But because you know what you need to make the cake, you search out the ingredients, apply them in the ratio needed, and then put them together in specific ways to make it look like a cake. Think of a scenario as the ingredients. We then look for the ingredients and apply them the way we need to, and then the result, the algebraic expression or equation, is a nice, tasty cake. Let's try that with our math expression. What are the ingredients or elements we need to make our algebraic expression? 1. Variables or numbers or both. And 2. Operations. Remember, we may not see all three, but we definitely must have at least one operation and two variables and or numbers. Let's identify our elements in the statement. There are different words that either give us an idea or clearly state what the elements we are looking for are. So let's take it word by word. The first word that gives us an idea of one of the elements we need is the word sum. When you think of the word sum, what comes to mind? If you said addition, then you're right. The word sum literally means the answer you get when you add two or more numbers. So you could say then that the word sum indicates the operation for this problem, the operation being addition. So I'm going to go ahead and make a note of that. Now, naturally, we know that in order to get the sum of something, we need two or more terms, numbers, or variables to be added. We call them addends. If you notice carefully, those are the last components of an expression that we need. The statement told us what those two addends are. Can you tell what they are? X and 7. Now, I can go ahead and place those terms on either side of my operation, the addition sign. I now have all the elements of my expression present. I need to now check to see if there are other elements of an expression left in the statement. Because there are no more components that we haven't already used, we are done. Just like that. Let's try another example. 8 less than y. Remember, our first step is to look for the components of an expression or an equation. Do you remember them? The first leading or suggestive word we encounter in the statement is 8. 8 is a number, which is one of the components we need to make expressions and equations. So, we go ahead and make a note of that. Next, we see the phrase less than. Now, at first glance, you might be thinking of what we call the less than sign. This is what we call an inequality sign that is used to compare values. For example, we could say that 5 is less than 10 or 29 is less than 150. However, if you read the statement we are working with again, you will notice that it did not say 8 is less than something. It wasn't a comparison of the value of 8 and another number. Instead, it is telling us that we are taking 8 away from something. That may not make a lot of sense at face value, so here's a trick to explain it. All we have to do is apply the principle we learned in the last session. Substitute variables for numbers. Because our aim here is merely to test a theory, we can use whatever value we choose. So let's say that the value of y is 12. Then the statement would read 8 less than 12. What value is 8 less than 12? 4 is. 4 is 8 whole values or places below 12. We get that by saying 12 minus 8. Another example would be, I have 7 pens and you have 2 less than I do. How many do you have? 7 minus 2 is 5. Therefore, in our problem, The phrase less than suggests subtraction. And just like addition, we usually have two or more terms to subtract from each other. But it's important to know which we must subtract from the other. Since it states 8 less than, we know that we are subtracting 8 in the same way with our other examples. The number we are subtracting comes right before the phrase less than. This number we call the subtrahend. The subtrahend is the number we are subtracting from another number. Therefore, we put our subtraction sign before our 8. Next, we see the variable y. That's the last component we need to complete an expression. So we go right ahead and place it before the subtraction sign. Now, we check to ensure we haven't missed anything. And since we haven't, we're done. And yet they say math is hard. Let's do 2 more examples before you try some on your own. Yuri is P years old. Raymond is 2.5 times as old as Yuri. Express Raymond's age in terms of Yuri's age. Why don't you give it a try first? Go ahead and pause the video if you need time. Now let's go through it together. Based on the wording of the statement, we can easily identify our variable as P. The number as 2.5, which is the same as 2.5. And the operation is times. And when we hear the word times in math, what operation do we generally think of? Multiplication. We've gone ahead and written those down so that they look a lot less like words and more like a math statement. But with this problem, we also need to consider that it comes with specific instructions. We need to identify Raymond's age, and we need to make sure that how we represent his age involves Yuri's age. That means one aspect of the problem is dependent or reliant on the other. In this case, we must be able to express Yuri's age in order to know Raymond's age. We know that Yuri's age is P, or variable. We then use that now to figure out Raymond's age. Raymond is 2.5, or number, times, or operation, Yuri's age. Put that together and we get 2.5 times P, which we can write as 2.5 P. That wasn't so bad, was it? Notice that even though the problem got a little more complicated, the concept remains the same. Firstly, we need to identify the elements of an expression or equation in the scenario. And secondly, we simply write them down the way we would in a normal math expression or equation. Let's take our final example. This one is going to be a little more technical. I think of a number. I then subtract 6 from it and multiply the difference by 4 and got a result of 36. Why don't you give this one a try as well? Let's identify our parts. The phrase a number is not an actual number. We ask ourselves, do we know what the number is? Since we don't, we use any variable to represent it. Let's work with y. The word subtract is our operation, which is pretty straightforward. The number 6 is right there beside the operation, so that's a number we need to use. The word multiply tells us we have another operation in this problem. So far, we have 2 operations. The word difference means the answer we get from subtracting. We already have our subtraction sign written down, but this part of the problem tells us that we need to do something special with the answer we get after we subtract. That's going to be important to remember. Next, we see the number 4, so we make a note of that as well. Then, we see the phrase got a result, which means that we are talking about an answer. When we are about to write an answer to a problem, what do we usually write before we record the actual answer? An equal sign, right? So we go ahead and make a note of it. Now that we have an equal sign, will our solution be an expression or an equation? Equation, because an equation includes the use of an equal sign. And finally, we have the number 36, which is our number on the other end of the equal sign. Whew! That first step was a little longer than the other examples. Nevertheless, you will notice that the procedure is the same. We just had to do it more often than we needed to before. All we did was to identify the aspects of the equation and then wrote them down. What's next? Right, putting them together. We started off with the variable y. Then, we were told to use our operation, subtraction, so we go ahead and write them together. Next, we were told what our subtrahend was. It was 6, so we go ahead and write that in as well. Then, we come across our next operation, multiplication. We go ahead and add that to our equation. But, what are we multiplying? We are told that we are multiplying the difference. We know that the difference is the answer you get when you subtract. What did we subtract? Y minus 6. But we don't actually know what the answer to that is. Still, we can use our expression as the difference. Let's explore that idea briefly. If we had the expression 5 minus 3 to solve it, we would write equals 2. That gives us the statement 5 minus 3 equals 2, which literally means 5 minus 3 is the same as 2. Therefore, we can use the expression 5 minus 3 the same way we would use 2. For example, we could say 3 times 2 gives 6, or we could use the entire expression 3 times 5 minus 3, which also gives 6. This is actually what we are going to do with our expression in our final example. We need to multiply our difference, and our difference is the entire expression y minus 6. To show that we are using the entire expression and not just a part of it, we place it in brackets. Next, what are we multiplying y minus 6 by? There it is, the number 4. So we go ahead and place that there. Almost done. Now we come across our equal sign and we go ahead and write that down. What goes on the other end of the equal sign? It's right there, 36. And we're done. I'm going to, however, rewrite this equation without actually showing the multiplication sign, simply because it looks nicer. Plus, we need to get used to seeing it appear this way, because it is generally the most acceptable mathematical way of representing it. You will notice that it was easy to formulate the equations and expressions in our examples because we started by identifying the components first. So, all that we needed to do was to fit them into place, like assembling the shapes of a pattern box. Now that wasn't so bad, was it? When we return next time, we'll explore how we actually use this kind of knowledge to solve problems by solving linear equations. But, as usual, I never leave students without questions to practice. So, accompanying this tutorial video is a set of problems you may use to practice and master the ability to create your own algebraic expressions and equations. As usual, don't try to do them all at once. Stagger them in manageable chunks and spread those chunks across the week. Thanks for joining us, and see you next time.
I like stunning. I like